No, it's good to me.
Well, who knows? All right. So this is a slide where everybody who has come to these has seen this many times. It's just echoing what Tom said, really. We want to hear from you. We do have this channel on the CPP Lang Slack, so please go and join that and chat to us, and that way we can, communicate for the 6 days a week we're not here. So yeah, that link's there. These slides will go up on the GitHub after the session, as always. Okay, so today's lesson plan, we're going to, well, the introduction was about smart pointers, but if we're going to talk about smart pointers, we have to sort of take a step back and work out why we want smart pointers. What do they give us? So we're going to talk about some sort of kind of low-level ideas about object lifetime and that sort of thing. We're going to mention stack and heap briefly, and then we're going to crack on and talk about smart pointers. I have to apologise to you guys. The reason I was running a bit late actually was you were supposed to have 2 exercises to do today, but I messed up. Basically, I found a pretty major fundamental bug in the second one, so there isn't a second one. We may end up finishing a bit early because I did budget quite a lot of time for that. So apologies, that was my fault. I think probably what we'll do is I'll try and I'll clean up and get it working, because it was pretty in-depth exercise about shared pointers and breaking reference counts and class hierarchies and stuff. So I'll try and clean that up and get it working, and let all the answers thrown for a second. And I'll get that working, and perhaps the first session next year, which sounds like a long time away, but it's not. First section next year, we'll have one of our sort of group exercises and work on that. I'll kind of add to it, and because I think if I get it working, then it's a pretty good exercise, and it will tell you quite a lot about shared pointers. So I haven't got quite as much as I wanted to have today, so apologies for that. But we'll see how it goes. The other thing is I can't actually see my presenter notes on the screen, so I'm just going to have to make it up as I go along. So if I and so on, that's... Yes, all right. So object lifetime in C++. Object lifetime. The lifetime of an object sounds obvious, but it's worth getting the definition out of the way. It's the time between when an object is created and when it's destroyed. Right? It's the time when you can use it. That's simple enough, right? Some nodding would be good. Yeah, come on.
Sorry, I was typing the link to the people so they can follow us on chat.
Oh, don't. Anyway, nervous enough as it is with people watching me online.
To be honest, it's only one person, I think.
Well, even so. Hello to whoever you are, by the way. Right, C++ doesn't have garbage collection. Hey. So unlike many other languages, C++ doesn't have garbage collection. Right, this means that we need to worry about object lifetime ourselves. So languages like Java, you just create a new object and you use it, and at some point you've stopped using it and the runtime cleans it up for you. You don't have to worry about it. I said C++ doesn't have garbage collection. That's not quite true. You can get garbage collectors for C++, but to be honest, they're not very heavily used. If you want garbage collection, you may as well use a language that's designed for it, like Java, C# or what have you. Well, I think of it as garbage collection is a bit like having an automatic gearbox on your car, right? It's great when you just want to, if you're driving a Ford Fiesta and you just want to poodle to the shops. Automatic gearbox is great, but Lewis Hamilton drives a manual. You know what I mean? If you want a race car, you want ultimate control, you want a manual gearbox. It's more to worry about, it's harder, but it lets you get that ultimate performance, which is what C++ is all about. There are 4 kinds of this is where I don't get my notes, so it's a bit annoying because I was going to ask you about this, but too late. 4 kinds of object lifetime. We have automatic lifetime, static, thread local, and dynamic. Did you guys know that, by the way? You did? Okay, well, whatever. I didn't know this till I I was looking on CPP reference, making sure I was teaching you guys the right stuff, and I was like, really? There's 4 kinds of these. So there we are. So automatic lifetime. So for those who has been to all of them? You haven't yet. You had a couple of weeks off, didn't you? Yeah. But basically in this course, so far, we've only dealt with automatic variables. Or objects with automatic storage duration. Storage duration is the sort of technical C++ standard term for this. They're normal variables, the ones you declare in a function, right? So you say int I equals 0, int I equals 0. It goes away at when you leave the function. So yeah, the lifetime extends from the pointer declaration until we exit the scope. So none of this is revision, right? This is, if you remember way back in the very first class, I said this was the very best thing about C++. And I maintain that, it is. This shouldn't be surprising. These are everyday common garden objects that we use. Right? Should be 99% of the things you use. We also have static and thread lifetime. I'm not going to say a lot about these. So static objects runs from the point of definition until termination of the program. So the destructors for your objects run after main is completed. Usually, there are a few ways a C++ program can terminate that doesn't actually run the destructors, but we won't worry about that. And thread lifetime, again, that's pretty advanced stuff. We're not going to worry about threading too much, but just to point out, thread local variables exist. So you declare a static object, or inside a function anyway, you need to use the static keyword, or thread local for a thread local object. Just be careful, because static means lots of different things in lots of different places. So if you've got a variable that's outside of a function, so at namespace scope as it's called, then static, they automatically have static lifetime, and if you use the static keyword, that's actually about linkage, about visibility. So it's not about lifetime. They automatically have static lifetime. It's syntax. And also static member variables are different again. They also have static lifetime. Tricky. Yes, I know static is probably the worst keyword in C++. It has lots of different meanings.
How about auto?
Auto is the best keyword in C++.
Auto pointer?
Don't ever say those words again.
They never mention auto pointer. It's not real.
Right. And finally, we have dynamic lifetime. Oh yeah, predicting myself. So objects with dynamic lifetime, you use the keyword new to create them, and then you destroy them with delete. I'm waiting for one of these guys to smirk. This is a slight simplification, I know, but this is what we're going with for today. Right? You can use placement new and manual destructive calls, but that's how we're going with it today. You can create an array with a dynamic lifetime using this array new, so new with square brackets, and then you have to pair it with a delete with square brackets.
And if you don't?
I said this is the golden rule. I don't think golden rule is strong enough. I think it's the platinum rule. Every new must be paired with a delete, and every array new must be paired with an array delete. This is
Bitcoin rule.
the Bitcoin rule.
Yeah, not platinum, Bitcoin.
Oh, well, it's probably worth more than platinum now, isn't it? Right now, when I'm saying this, I suppose if we watch the video back in a couple of months' time when Bitcoin's worth $2,
Yeah.
when the bubble bursts. I'm not kidding, I'm just gutted, I don't know.
Anyway, so let's stick with
Move
platinum.
on. Oh, yeah, sorry. So, yes, this rule is absolutely key. New with delete, array new with array delete. Everyone got that? Okay, good. I'm going to test you on it later, all right? Right, let's go on and talk about the stack and the heap. Again, these guys are going to complain because I'm not being, this is a simplification, right? It's a way of thinking about this, that's not completely accurate, but it's enough to get an understanding of it. And if you're really dead interested in function call APIs and things, you can read about it. But yes. So local variables with automatic storage duration are allocated in a memory area called the stack. The stack is a pre-allocated bit of memory given to a program by the operating system when it's launched, and it's typically quite small. So 8 megabytes, I think, is the default on Linux. I think, is it 2 megabytes on Windows? Anybody know? Default stack size. There are various operating system specific ways of changing the stack size when you launch a program.
In Windows, it's in the PE header. You have a custom stack size in the PE header. That also applies to threads as well. So thread has its own stack. Carry on.
Every thread has its own stack, yes. May or may not be the next bullet point.
Every C++ thread has its
own stack, yes.
According to Google, the stack data is 1 gig, the stack size is set by the linker, and the default size is 1 megabyte. That can be increased using linker property system stack reverse size. Note that on 32-bit Windows, the sum of all types data must be 2 gig or less. And that was written in 16 May 2011.
Okay.
Sorry.
Yeah.
So each thread will have 8 meg stack.
Yes. By default.
So you can sort of get around that stack is relatively small. 8 meg exhaustive will crash your program. So if you wanted a bigger stack, say, I don't know for what reason, but you could then just use multi-threaded too.
But you can't. How do you move data between threads? You can only copy it from one stack to the other, right? So if every thread is doing completely independent things, but the point is you have to be very careful about your stack usage, right? You can't go allocating multiple megabytes, big. So standard array is a standard library container wraps around a raw array, and it's allocated on the stack. So you don't want to be sort of a small, like, well, kilobyte would be fine, but you don't want megabytes of data in an array, right? It's pretty dangerous. Every thread of execution has its own stack. Stack allocation is very fast. Very, very fast. It's pretty much just moving a pointer, or updating a pointer value, and then calling constructors. But it's limited size means we can't use it for large objects, as I just said.
Sorry.
Yeah.
So if I've got, say, if I'm looking at a very, very large data set with millions of rows, say I'm reading it in from another database.
Yeah.
So how would you suggest what should my data structure be within my program? As in, if you don't think I should use.
Well, if you need, if an array is an appropriate data structure, then use a vector, because a vector it uses dynamic allocation, which we're going to talk about quite a bit in the next few minutes. So dynamic objects with dynamic lifetime are allocated on the heap, not on the stack. It's also called the free store. It's a bit confusing actually, because stack and heap, as well as being these memory areas, are also the names of data structures. So you can end up with a stack allocated heap or a heap allocated stack. And I think the dual use sort of goes back to kind of the 60s, and they used a stack data structure to store the stack and heap data. I don't know. They've got dual meanings in computer terms, and that's a bit unfortunate, but there we are. The size of heap allocate, the amount of heap storage you have is theoretically, anyway, limited by the RAM on your system, right? So as opposed to 8 megabytes, you've probably got modern laptops like 8 gigabytes. Even my phone's got a couple of gigabytes of RAM now. It's crazy. I say in principle because there are various ways of limiting how much memory a program can actually use. On Linux, you can do the opposite. You can actually ask for more memory than you actually have on your system, something called overcommit. If you try using it, then bad things happen. But anyway, heap allocation is much slower than stack allocation. The reason for being is that we have to go and we have to ask the operating system, can we have more memory, please? And it'll find a bit of memory no one else is using of the right size. It has to lock lots of data structures to do that. And hopefully it'll come back and say, yes, here you go, here's a pointer to this raw bit of memory. Oh, sorry. I think I've made a mistake. Never mind. Yes, I'm sorry, there was supposed to be, back when we were talking about new and delete, there was, just imagine there was a slide there that was telling you that operator new returns a pointer, a raw pointer to some memory, and delete takes a pointer. So new gives you a raw pointer, you pass that to delete. Array new, on the other hand, gives you a pointer, right? So there's no way of knowing, if you've just got this pointer, there's no way of knowing in advance whether you have to call delete or array delete on it. Rather unfortunate.
You think that also a compile, right? The compiling and telling.
No, in general, as far as I know. It may be, I mean, Clang's got super advanced warnings, so Clang can do ultra clever things like, if it sees you doing new and delete in the same scope, it will take those away and put things on the stack for you. It's actually, Clang is kind of amazing like that.
Yeah. How does array delete know how many elements?
That's a very good question. Very good question. It's implementation defined the way it happens, I believe, on Linux at least. It actually puts the size first. So it allocates this thing, puts the size first, and then the pointer it gives you is actually, so imagine, got no whiteboard. Oh, I've got a whiteboard.
There is a whiteboard there, yeah. I need to turn the camera back on there for that. One sec.
So, imagine you ask for an array. So you say,
What are you looking for? I had it in my hand and I was using it. I can't focus it.
you said new int square brackets 4. You want 4 ints. It will return you a pointer, but what it secretly does is just before the allocation, this thing will contain the size. So this thing will actually be 4. And then it will return you a pointer to this thing. It will return you a pointer to the first element in the array. And then when you call array delete, it'll actually look slightly backwards from the address you've been given and see the size. That's how it works on Linux, but it's all implementation defined. That's how I think it works. I'm not an expert on this.
This or something else.
Just a question. That's a weird looking data structure, isn't it?
That's just supposed to be an array. These are supposed to be
but if you're new in a chart and you have a array length that's a long,
the array length is it'll probably be 4 bytes on a 32-bit system and 8 bytes on a 64-bit system.
So then the length of the size of the information is different from those.
Yes. But the operating system,
Yeah, so they can see the board.
the operating system is going to know how big a size to expect to look for. Right. So let's get rid of that. That's scary, terrifying. So, by the way, don't take that as gospel. That's back in the back of my mind, memory of how it does it. It may be different. It's, as I say, the C++ standard doesn't say how to do it. It just says it must work like this. That is one of the schemes I think is used. So, yeah. So pros and cons. We need to. Pros and cons of automatic and stack variables. So they're very fast to create, and the compiler manages the lifetime, right? This is what's brilliant about them. Not the fast to create, I mean, that's nice, but the compiler managing the lifetime for you is Great. Unfortunately, we can't have megabytes of data on the stack, so we can't have gigabytes of data. It's just not going to work. On the other hand, we have unlimited, not really unlimited, but a large amount of memory available. It's also necessary for runtime polymorphism. So this is something I haven't really talked about. But if you have like a base class, like an interface, and you have an implementation, if you want to, and there are good reasons for doing this, if you want to hide that implementation, if you want to make that implementation private and only have people deal with the interface, well, then they're not going to know how big the implementation class is, right? So you have to use, in that case, you can't allocate something on the stack if you don't know how big it is. So in that case, you're going to have to use dynamic memory management, and you pass a base class pointer back to the user. Right, so that's one of the main uses of dynamic variables. And also, they're slow to allocate. Slow is a relative term. Slower, I mean, it's not really slow to ask for in the grand scheme of things, but it's probably not something you want to be doing millions of times a second. Right. Plus, we, in principle, at least need to manage memory manually using new and delete. Everyone clear the difference between? So these terms, stack variables and heap variables, they're a bit imprecise, and pedantic people will correct you and say, I think you mean an automatic variable. But just in sort of casual conversation, you can, or at least I use those terms. Right.
If you want to break the pizza, by the way, find it.
Yeah, I will. I like this. I want to come up with more keywords, potentially perilous programming pitfalls.
Nice.
Yeah, that's what I should have gone for. Anyway, failing to delete an object that we created with new is a memory leak. That's bad. What's even worse is deleting an object twice, or trying to delete an object twice, or mixing up delete and array delete. That's almost certainly going to crash the program.
Sorry.
Yeah.
Maybe a bit of a naive question, but first point, failing to delete an object created with new is a memory leak. That is bad. How bad is bad? As in, I presume you would need an accumulation of these right before your program crashes.
Well, your program's not going to, it's not going to crash until you exhaust the whole operating system's memory.
Yeah.
But if you're doing what I said, if you do allocate millions of things a second, it's not going to take you very long to do that. And meanwhile, your system's ground to a halt. If you're running Linux, the out-of-memory killer will come along and start killing random processes, not necessarily yours, but just random things that you haven't touched in a while. Things will start paging to disk, everything will, no, it's bad. It's bad. There is an amusing story that I may as well tell this. We've got a little bit of time today. There's some code for a guided missile, launched from a fighter or from a bomber. They were doing some code review on it. They had an external person come in, and he said, "Look, you've got massive memory leaks here. You're calling new everywhere. There's not a single delete in your program." Like, yeah, but it's running on something that's gonna crash. It's gonna explode. We have the ultimate garbage collection. This is the second most important bullet point today. Most important one was the golden platinum rule, right? This is probably the second most important one. Ensuring that your program calls the right form of delete exactly once, exactly in the right place, is a very, very difficult task, right? Do not underestimate how difficult this is. This was what you had to do in C++ 98, for the most part. And you had that paper about how to write an assignment operator. It was incredibly difficult. We haven't really talked about exceptions, but exceptions make this much worse because Exceptions mean that you can't really be sure of when you're going to exit a function. So if you really want to be exception safe, you either have to use smart pointers or wrap everything in try and catch blocks. Right? It's really hard to get right. And it's one of the major reasons that people dislike C++. So it's one of the major reasons that people invented garbage collectors, right, is because this is really hard to do. And so Java and C# and whatever, they have this whole subsystem running in the background that takes care of this for you, right? Because getting it right is hard.
Put the deletes in your destructors, effectively.
Yeah, but automatic variables are wonderful. Wonderful, I love them. Right? I don't know if I've conveyed my enthusiasm for these things enough. The compiler will ensure they're destroyed no matter how we exit the scope. So even if we exit the scope through an exception, so usually you exit the scope either by running off the end of it or with a return. But an exception, if you call a function, that function throws an exception, you'll pop right out and the bubble up through all the stack frames until the point at which it finds a handler. And if there's no handler, it'll terminate the program, but that's by the by. The automatic variables are great. Wouldn't it be great if we could use an automatic object to sort of manage the lifetime of a dynamic object?
Oh, would be.
That would be wonderful, wouldn't it? So let's try it. Let's have a class student. I'm going to class form. I was going to call it class, but that actually got really confusing. So form, right? Which holds an array of n students. This is something I didn't mention. Probably should have mentioned it earlier. You can't, in C++ anyway, you can't have a stack allocated array of runtime size. You can have a stack allocated array of the size you know at compile time, right? But you can't have the user give you a value n and have a stack allocated array of n objects. Sorry?
Allocate.
Which is not C++, POSIX.
Yeah, carry on.
C99 lets you do this. C11 made it optional again. Various proposals have come in about allowing this in C++, but as of C++ 17, you can't do it. So yes, if you want an array of runtime size, runtime determined size, you need to use dynamic allocation.
Sorry, I don't quite follow that.
Sorry.
Yeah, I didn't quite. So if you wanted a, yeah, so I still understand.
So let's say we're reading the register in from a file. So this is for our form, right? So we've got the names. Ahead of time, we can read this file, and right at the top of the file, it says there are 30 students in this class, right? But we don't know that value at compile time. When we compile our program, we don't know how many students are in the class because that information is in the file that we're going to read when we run the program.
Yeah.
Right? So we could for safety, like if we wanted to, and this is a technique some people use, is to say, well, we know that there are never going to be more than 60 kids in the class, and we'll just allocate an array of 60 and see how many we use. That is a technique. So if you need sort of ultimate speed, if you have to use stack allocation for speed purposes, that's one way of doing it. It's dangerous because what happens is, one day someone is going to have a class with 61 students in it, and your program's going to crash.
Yes.
And it's wasteful if you have, let's say, class of 5 students.
Exactly. But it's a valid technique in certain circumstances, but you have to be very careful with it.
So to think of it this way, physically there are ways to do it. You could combine alloca, which will dynamically decrement the stack by however many bytes you want, and you could use something like placement new to then instantiate an object in it. But you're mixing C and C++ when you do that. But physically it's doable, yeah.
Right, so if we want the class form, which has n students, where n is a runtime value, we don't know what n is when we compile our program, we need to dynamically allocate an array. So, okay, we dynamically educate it using this array new in the form constructor, and then we call array delete in the destructor, right? Easy. But we also have to handle copy construction, copy assignment. And in C++11, you have to handle move construction, move assignment. And you have to worry about getting everything right in the presence of exceptions. Because it's array new, if it can't allocate for some reason, it will throw an exception. Unless you set certain compiler options, or we'll call it with a no-throw argument, in which case it will return null. But by default, it will throw an exception, which is a bit of a problem. But there's a better alternative. We can use standard vector. So standard vector, you can say, you have a standard vector angle bracket student, and you just say, give me a vector of 30 students. Give me a vector of 30 students, right? And then you have a member variable that's a vector. And when you copy your class, the vector copies correctly. And if one of your students, for whatever reason, throws an exception when you're trying to construct it, vector will handle that. How exactly it handles it is pretty complicated, but it will do the right thing, right? It will never leak memory. It will always leave the vector in a valid state. So it handles the elements, the element construction, throwing exceptions. The default move constructor is going to do the right thing, the destructor is going to do the right thing. Vector is brilliant. Never ever use array new. That's the lesson. Always use standard vector.
So it's easy to say, safe to say that vector is preferred type over an array.
So standard array.
Yeah.
Standard array is useful when you know that something has a fixed compile time, fixed size, and you know that the object is small enough to go on the stack. So if you've just got an array of 4 ints, well, int is small, 4 of them are only going to be 16 bytes. You've got 8 megabytes to play with. The 16 bytes is going to be fine.
As general advice, I mean, like life advice. I mean, like for let's say new developer, yeah. So would it be safer to say stick with vector and you'll be 8 out of 10 times correct? I mean, would you think?
So vector using array, vector versus array, they have slightly different semantics, right?
Okay.
So you've got to use the right type for the right problem. So with an array, you've got a fixed size, it never changes, right? You can't grow or shrink it. You ask for 4 things, it's going to have 4 things in it.
Mm-hmm.
They'll be default constructed or whatever. Which is slightly different from a vector because a vector has a variable size. So let's say you pass a reference to an array to a function.
Mm-hmm.
When you get that, when that function returns, you know that that array has still got 4 things in it.
Okay.
Right? Because that can't change, it's fixed.
And you can have a pointer as well to an array.
Well, I'm talking about standard array. I mean, yeah.
Oh, you can, I think you can. Am I correct?
You can
There's like a pointer or anything.
You can of course have a pointer to a standard array.
Vector, that would be a bad idea in case the vector reallocate.
Oh, I see. You're talking about the internal data. Yeah. So if you call the .data member function, yes, you're right. So the invalidations, as they're called, are different between array and vector. That's another one of those differences. So use the right tool for the right job.
Okay.
I will say that you're saying, you know, for the incoming developer, the new developer, you said 8 times out of 10. I would go so far as to say 9 times out of 10. Vector is the tool you want, right? It's the tool for most jobs, right? This actually, as time has gone on and computers have got faster, and in particular as caches have got bigger, vector has become more important because vector provides superb cache locality. Because if we look at that little thing up on the board again, you can see all the elements are laid out in memory next to each other. So the compiler can, or the operating system, preload these things, put them all nicely in the cache for you, and you can just zoom straight through them. Whether it's something like a linked list, you've got to jump about all over different parts of memory. So whenever you can use vector, it should be your go-to data structure that you think of first. So in this case, yes, we've got class students, we've got a class form which holds n students. We could go do all this nonsense, but someone's taken care of it for us. Lovely standard library people have come up with this type vector. So as I say, behind the scenes, vector does all the hard stuff, deals with allocating, copying, resizing, deleting, etc. Behind the scenes, it's effectively, I mean, it's a bit more complicated for standard library classes because they have this allocator thing, but effectively it's somewhere calling something like array new, and somewhere it's calling array delete. So it's a great example of using an automatic object to manage the lifetime of a dynamic object. Just what I'm trying to introduce you to is, you already know this, you've all used standard vector. I know this because we've done the exercises. Right, so standard vector behind the scenes is doing all this nasty stuff for you, but it hides it. It's hiding the use of a dynamic object, or dynamic array in this case, hiding it behind a nice value type interface. And that's just the principle behind smart pointers. So smart pointers is using an automatic variable, a variable with automatic lifetime to manage a dynamically allocated object. Same principle as standard vector. Not scary at all. That's pretty much what I just said. I can't see what's coming on my slides, by the way, so I'm ending up repeating myself, so apologies for that. So C++ 11, we have two smart pointers. So boost has a few others. We have unique pointer, or unique putter, some people say, and shared pointer. I think it's pointer, yeah. Stood shared putter, if you're
That sounds like
this is
swearing.
Yeah. C++98 had an earlier attempt at a smart pointer called auto pointer. Don't ever use it. I should have put that in red or bold or something. Don't use auto pointer. It's actually been removed from C++17. Was it removed from 14?
No.
No. Well, it's gone now anyway. Don't use it. Don't try to use it. It's wrong. It's bad. It won't work. Okay. We're going to write a smart pointer. A really simple one. This is the exercise that works, by the way. The other one, well, we won't be doing it, so don't worry about that. This one hopefully works. We're going to write a simple smart pointer. So we're going to use the principles I just said of using the constructor, the destructor, the copy constructor, etc., to create a type that behaves like a raw pointer, but behind the scenes manages a dynamically allocated object. So this is the usual business for you guys. There's a little test program called runs catch. I've created a skeleton of a class for you, and each member function has some comments telling you what I want that member function to do, and your job is to implement that. And if you get really bored,
I mean, I'll just introduce and disturb a little bit because we'll have now some work to do. So just have some break. I mean, you're very welcome to jump and grab a slice of pizza or more before it gets cold. And obviously,
there's two jobs.
Let's do I know it's difficult for some people to multitask, but try your best. Yes, eating pizza and so on might be extra challenge. You will meet in your day-to-day work.
Reading, eating, and drinking.
That's three things.
3 in 1. Who can do it?
And if you add to that thinking about what you're writing, even better.
Oh, it survived. It survived. Sorry, give it here. I'll solve it.
So when you create an example, create an array, say for example, array of doubles, double open bracket, close bracket, square bracket. Yeah. So yeah, square bracket equals new. And you have to
no, sorry, you do double star, because new, array new, both ones are new. return double star equals new array, new double square bracket.
And that's something we should never do that.
Well, because we've obviously saying never really.
Yeah.
But prefer a standard.
Yeah.
Very little reason ever to use array.
Yeah, if anyone has questions who are watching, then feel free to ask them in the chat and we'll read them out and one of us will assist you.
Yeah.
We've already got one cloning the repo.
Might be one of these guys.
Oh, did you just type OK cloning the repo now? No, no.
Oh, I really hope this works.
Well, it's a bit of an experiment, right? It's the first time we've done it at this scale.
Well, yeah, I mean, we will, expand if we got access to something like this next time and next time and next time. Then we'll learn more things.
Yeah. No, I'm all mean because I forgot the second exercise. I'm now worried the first one might have the bugs in.
We'll fix it as we go along. Oh, we did have a question from earlier now, since we're also waiting. Devereux asked, can stood shed pointer be considered a close approximation to garbage collection?
And keep watching.
Oh, okay, that's coming. Okay, that's coming later. There you go.
How do you use Minecast to pay for the beans?
can do tomorrow class.
Just ask it as a
It's personal charm audio.
Yeah.
Yeah.
The funny thing, but
Just waiting now.
the funny thing is, if I run the test, yes,
Yeah.
without the second part done, I got test state, space, and so on. Yeah, so it'll be fine. Enable this.
Someone's gonna,
No, it's fine. Two cases.
that's because it's crashed.
Ah, okay.
So it got as far as running the second case and then crashed.
So is my case incorrect?
That is incorrect, yeah.
Ah, okay, cool.
Right, so you want to create a new dynamically allocated int. So that's a clue that there's probably keywords you need to use.
New.
Yeah, exactly.
Also, just a quick point as well. If any of these solutions, we want to have them talk through them, then they should get the Zoom app so they can share it, and then obviously everyone can see and all that good stuff.
Okay, what I was going to do for this one actually was the solution's already on GitHub, so
Oh, okay.
I'll switch screen to somehow. Anyway, switch to
Okay.
GitHub and we talked about implementing shared link pointers. Decided that was probably going to be a bit hard without knowing about some templates. So, what's nice about an int is it comes from classes, so you can just have a copy constructor.
Yeah, if anyone's hungry who's watching at home, we're really sorry for making you even hungrier.
Well, they can always join us in London.
Yeah, you can always come join us.
Now, you got the ungated Wi-Fi?
No, yeah, but I think currently.
That might be.
Definitely not. No, it's under the crap.
I was going to have one of those, but you nicked the last one, but now I've just got Guinness. I'll probably finish it. I'm doing a lot of talking, I get a dry throat, you know? Swanky here, isn't it? A bit huddled around the TV with the stereo on.
Okay.
Yeah, all right.
I'm trying to remember how to use the new technique for so long.
Yeah. So you say new, and I say new, and then a type. And then brackets.
Okay, that's what I was thinking. Thanks.
say new, and then a type, and then you put the arguments in brackets after it. Curly brackets there as well. And this will return you a pointer. Type you specify there.
You go to the far side, then it's easier to look.
That actually works with brackets.
Yeah. Okay. Focusing. Ish. They've run out. Start from. I looked. Anything else you like?
Let me go through the beginning.
There's several templates.
I like that.
Oh, IT spin. IT spin. Or something else. Must be a Hitchcock fan.
You could say we're in a paradise. Working on the PC, socializing with people, eating pizza, drinking beer.
It's on heaven, isn't
IT.
You've got the strippers.
Mm-hmm.
it? Yeah, well, come on.
2.5 gigs.
Is everybody in the Zoom audience doing okay with the challenge? I should be able to read it on yours as well, but I don't know, read one. They're all hard at work coding.
You guys just copying pizza.
Mm.
Oh, you're on.
It's the unofficial one.
So who's managed to crash the test program so far?
Crash it, yeah.
Only yourself? Oh, you guys are just pros.
It compile, ship it.
Yeah, exactly.
Who's managed to pass all the tests?
Almost.
I'll be honest, I was expecting more questions because you guys are getting pretty good now, so I'm giving less and less information about how to, fewer clues, how to do these things. But you're plowing on regardless. So
Why did you make operator bool explicit?
it's a very good question. Because bool, unfortunately, is implicitly convertible to almost everything. Int, unsigned int, long, size t, everything. And
Wait. No, it's not that. I'm saying the type is going to be int pointer. If you make
I made a mistake.
If you make it explicit, will it not fail if you do if if int pointer t? If you do if t, will it fail now because you said explicit? Because it will say you must
no,
can't sit to bool.
no, because in an if statement, that's one of the cases where you convert it to an if special case. But yeah, C++ 98 had the safe Boolean where you'd actually return some anonymous function pointer type that couldn't be converted to an int. Because otherwise you can do crazy things like, int3 equals, and it would implicitly convert to bool, which was your one permitted user-defined conversion, and then it would have an automatic conversion, and that would be bad.
And there was the good old operator plus plus.
Yeah. Well, that wouldn't work because you can never call that on an R value, I think.
No, not on an R value, no. But you could, I think, if you had an L value.
Yeah.
They removed it.
So for the third one, is it possible to allocate the address of that? So that's a reference variable.
Yes, the other is a reference to a constant pointer.
Yeah. So it's saying allocating new dynamic allocated int.
Okay, so if you look right at the bottom of this class, it has this private member. Well, it should be private. I had to make it public for the tests. But so what you want to do is say, our member variable ptr equals new int, and then some value.
Okay, so
It's actually a bit of a workout on pointers as well from like a month ago now.
okay.
Remembering about dereferencing and all of that.
Yeah, ask you something. I should be deleting here or delocating because it's deleting. That's I was expecting this to work. But if it's delocating, so delocating to no pointer, then I was hoping this will work. But neither is this.
No.
Correct.
So what was the golden rule? Platinum rule. Every new has to be paired with a delete.
Yeah.
So in your constructor, you should be calling new.
You mean have this one.
Yep. Well, not the default constructor, so the value constructor. I'm calling new, and in your destructor, you want to pair every new with a delete.
Okay,
Now, the
so
compiler ensures that the constructor is paired with the destructor.
uh-huh.
So you have to make sure that the constructor, which calls new, is paired with the destructor.
So I need to create here with the new.
Well, no, in the, so, oh, that's probably something I should have mentioned, sorry. Yes, by the way, that's because I'm silly and I forget to mention these things, right? You can call delete on null pointer, does nothing. That's perfectly safe, right? Calling delete, null putter, null pointer, does nothing. So if you look right down at the bottom, the member variable has the default value null pointer. The member pointer has a default value null pointer. It's perfectly safe to call delete on that. It does nothing. Won't crash. It's perfectly well defined.
It's a waste of CPU cycles, but yes.
It's probably more efficient than doing if pointer delete pointer.
That's also true. My argument is more that in your architecture you should know it. You shouldn't be building it so that you don't know it's null. If it's something that's outside of your scope, then fair enough. But if it's within your design, then you should know it.
We've tried to replicate pointer semantics, haven't we? So default constructed what should be null.
Oh no, that's different. If it's outside of your scope, so you don't know,
Right.
then it's fine.
Well, this is an argument about using references instead of pointers as well.
Oh yeah, of course. Well, that's more an argument of object lifetime, right? If I'm using a reference, as long as I know it's going to be within lifetime constantly, then it's fine. What if it's not?
Yeah, I mean, like passing a raw pointer to a function. If we're going with the thing that raw pointer means, I don't know. Passing a raw pointer to a function means this thing might be null. Yes.
Well, it's still optional. Still optional.
Yeah, but the kind of optional references which I ranted about at the times. Guy who wrote Bruce apparently campaigned very strongly to the committee to allow optional TREF. But the trouble is the assignment operator of optional TREF is problematic. Whether it reruns or not.
Yeah.
Probably won't. Tell you all about it in the past. Sorry, did you have a?
Yeah, we'll ask some questions. Yeah, so the requirement is to dynamically allocate the instance value answer.
So you're taking the address of PTR. So PTR is a pointer.
Yep.
So you're taking the address of a pointer. Are you sure that's what you want to be doing?
So you talk about this line here, right? So I'm saying at that address I want that value.
Okay, so you need to dereference the pointer, not take it direct from your
sorry.
star rather than, yeah. No, you don't need brackets.
So you brackets.
Dereferencing it, you're saying the thing at this address, set it to I.
Same value as the other. With the same value, I probably making the same mistake there as well. Equal to 37.
So one thing I've noticed a couple of people is in the copy constructor, you're given a reference, const reference to another object. One thing you have to think about is what if this other object has been default constructed? What if its member pointer is null? Right? Because if you try and dereference a null pointer, things are going to explode. Right, so you, in the copy constructor, be careful. Copy assignment operator as well. So it's a good thing I didn't have to do these exercises because the language I'd use certainly wouldn't be appropriate. Like the language I was using when I was trying to fix things.
That bad. Sanitizers, man, sanitize.
You need to sanitize my
Sanitize your language. No.
sanitize my vocabulary.
Yeah. Sanitize both your languages, right? C++.
And English, yeah. I do wish I could speak another language just for those times.
Mm.
And the trouble is in London.
Learn some Dutch. Everybody getting on okay? Both here and online? If anyone needs any help, then let us know.
I think it's nothing else. This is good.
Same, so that's the same that applies to the assignment.
Copy assignment operator, yes.
So if you say not
Valid
equal
operator
to,
not equal null pointer. Die. Yes.
so it doesn't matter. That also applies to
Copy assignment operator, yes, absolutely.
so that's both.
Yeah, that's good. Well done.
For the assignment,
Yeah.
don't you have to check if that is already equal to this?
Yes, you do. Well done. Well done. Full marks. Help yourself to another slice of pizza. Yeah, that's another of these tricky things that I'm just a bit of revision for you. When we're writing a copy assignment operator, and this is going back to, I think, the second or third class we had, in the copy assignment operator, you have to be careful about self-assignment. And you have to be particularly careful when you're doing things like this, because you can end up deleting the pointer that you're about to try and copy.
So if you fail a test, how will you know which one?
It should give you the name of the test. So you can just click on that.
Well, if you crash it, that may not be the case, but
And you'll see, so it's trying to do copy assignment.
this one should still be, shouldn't it?
Okay, good. Thank you.
Wait, let me know when you're presenting again. I've stuck it on hold.
Yeah, I might just calculate.
Okay.
You done? Yeah. Passed all the tests.
Hello, world.
I did, if you look in the reading, I've got a bit of an extension if you want to start playing. Oh, is it not mandatory, but just if they're not interested in their own stuff. And the other hand, don't have to teach them.
I folded it. I did using input equals to unique pointer.
That's a copy constructor requirement.
Oh shit, that's true. It doesn't. Damn,
Doesn't
that's
have the
true.
right constructor either.
Mm.
Well, you can do like that. Research.
We can have a shape point member variable if you want to.
Yeah, that's true.
That's not correct.
Oh right, okay. Oh, you could use a unique pointer. Just have your copy constructor have a unique pointer as a field. Just copy out the value. Yeah, get your shape pointer.
Or would say shared? I mean,
Yeah.
Right, so I reckon 1 more minute, and then we'll
Play the countdown clock noise.
Yeah. That's actually something we should do. There's, do you remember that CCP London we had, where we had the programming exercise?
Yeah, those countdown.
They got on the YouTube, the
Yeah.
countdown.
Yeah,
You can open your machine if you want. They got like 60 seconds, 5 minutes,
oh
whatever.
no, so C++ London, one of the sessions, the main ones,
We had, I can't remember the name of the website now, but it's got sort of programming
Code
exercise.
Dojo.
Code Dojo.
Yeah. And it's
That was
quite a fun thing. Fun exercises. We didn't do all that well, did we?
Didn't do terrible.
You, me and Tony, I think.
Yeah, it was, crap, I forgot his name now. The bearded guy dresses quite nicely.
On our team, or?
No, he wasn't on our team, but he won.
Oh.
He got the one where he realised that override was a conditional keyword. That was brilliant. That was and final. Finally.
Okay, so I'm going to go through the solutions very quickly. Bojan sitting at the back all smug because he got it right. Everybody else, how far did you get? Sorry, not far.
3%, but fine.
All right. That gives me a chance to open the GitHub. It might. Do I have to go to the app?
Is it working?
I'm sorry, I'm just looking for Safari, which doesn't seem to be
Oh.
maybe it's because it's full screen.
Yeah, that's good.
Okay.
That's it. Perfect.
Everybody see this? It's 5 to enlarge the image. Scroll slowly. So we have this struct in pointer. And what I wanted basically was something that behaved like a pointer but deleted something when it had finished with it. So if we have a look, it's going to scroll painfully slowly on this display, sorry. Right down at the bottom, I've got this member variable. To pretend it's private, I just, for the sake of the test, I had to be able to access it.
Private public.
Yeah. So as you can see, I've used an in-class member initializer to set this to null pointer. So that means that in our default constructor, we can just say equals default. We can even put its own type of context for equals default. That'd be fine. So the constructor from an int. So the requirement is to create a new dynamically allocated int with the value I. We can do this in the member initializer list. Right, so we don't need anything in the body of our constructor. We can just say a member variable pointer as a value of new int. Now our constructor is called new, and we have to pair a new with a delete. Well, the compiler, as I was saying to Tom, the compiler makes sure that every constructor call is paired with a destructor call, right? So what we have to do is make sure that if our constructor calls new, our destructor calls delete. Right, so that's exactly what we do. And as I said before, with the default value of null pointer, delete nothing, delete null pointer is completely safe, so we don't have to put any guards around this. That's perfectly safe. Now we have a copy constructor. We can't use the member initializer list here because if other's pointer, if that has a value, So I'm doing an implicit comparison of the bool, of converting the pointer to a bool. So I should probably, for clarity, have said if other dot pointer not equal to null pointer, but that's what that means. And we say our pointer is equal to a new int, and then as its starting value, we dereference others pointer.
Should that be in the the square bracket or just normal brackets?
Square brackets would be arrays.
So not square, the
Parentheses.
Round parentheses.
Yeah,
You could do for an int, it would make no difference.
Okay.
This is, so basically these curly braces like this is the new nice syntax. Previously it didn't exist.
Universal constructor syntax.
Yeah, and the reason why is there's something called the most vexing pass. If you use parentheses, so say for example I have a class T, and I just declare T brackets, right? Or I can do like LT T lowercase t brackets semicolon. If you use parentheses brackets, then the problem is that if you forget to include the class file, that gets read as just declaring a function prototype.
Okay.
So by using curly braces, this is one example of how it's completely unambiguous. So these are a nice new addition to the language.
Oh, okay.
They're wonderful.
Also unifies construction between classes and aggregates. I actually think it sucks, but there we are.
There's always one.
Because of standard initialization. Look, we're getting off the point,
Go on,
right?
go on.
Let's move on. This one was actually a little bit complicated. So as I said, it's I'm terribly sorry, I've forgotten your name, but as he said, Peter, I'm so sorry. As I said, in an assignment operator, we have to check whether we're doing self-assignment. So the standard way to do that is to check whether this, which is the address of the object we're operating on, if this is not equal to the address of other, then we delete our current pointer, we set it to null pointer, and then if other has a value, if other's pointer is assigned to something, we do the same as we did in copy construction. Right? Does that make sense to everybody?
Yeah.
Yeah? So just hypothetically, what do you think would happen if we didn't have the self-assignment check?
It will crash.
Actually, I don't think this would crash. But the problem would be if this and other are the same object. Sorry guys online, but I'm pointing to the screen. If this and other are the same object, then our PTR is others PTR, pointer method variable. So when we call delete here, it's also deleting others.
So then it will crash.
So then when we get to here, well, others pointer.
Have you done the ternary operator, by the way?
Ternary.
Yeah.
I probably mentioned it in passing, but I haven't said a lot about it.
Oh no, I'm just curious because you could have done some pointer equals, other dot pointer question mark.
Oh yes, I suppose you could. Actually, you might be right, I'm sorry. Anyway, it doesn't matter.
I think I got this one right.
No, you wouldn't crash.
Oh well, totally.
So this returns true if and only if the pointer is allocated. I could have just said return pointer here, just to make it a bit more explicit. I said if pointer is not equal to null pointer. So possibly that makes it more confusing. But basically, if pointer is equal to null pointer, this thing will return false. Otherwise, it will return true.
No, I think that's clear.
Yeah. Okay. The dereference operator. We want to return a reference here. The reason is we want to be able to say star I equals 3, right? So we have to return a reference. The initial prototype was just int, because which I had to do because otherwise it wouldn't compile. So this is potentially unsafe for a smart pointer. So if we're using this, just like for a raw pointer, if we're using the dereference operator, we first have to check whether it contains a value. We have to do this Boolean check.
The risk is because you're returning the pointer. Yes,
yeah, so if we try and dereference a null pointer, so we're calling star on the raw, operator star on the raw pointer. Now, if that's equal to null pointer, we're going to crash.
What happens if the start point PTR, yes, when it gets to the last, the curly braces, that variable in that place will be destroyed. Am I correct?
Yeah.
Yeah.
Well,
No.
this gives you a reference, and then we're returning that reference. Right. So there's no local variable here to be destroyed.
Okay. So
basically in C++, dereferencing a pointer actually returns an L value reference. It doesn't return a copy or anything like that. It's an L value reference.
Okay.
That's how we're able to return the int ampersand by doing start pointer.
Get was very simple. This is just for symmetry with the standard. Which is reset again. We delete our pointer and we set pointer to this other value. So we're assuming that someone somewhere is called reset brackets new int. And that was that. So did people get close to that? I know at least one person did. People get something close to that?
I mean, I stuck on one of the first, so I didn't manage to go through. The rest seems to be okay, but
okay.
Also, just a point on the self-assignment check. Generally, in most of the standard, the STL, there's no guarantee. If you do any self-assignments with any object, it's usually, well, you shouldn't do that. Don't do it.
okay.
So this is a nice library for doing that, but don't expect it from anyone else. Yeah.
I'm just going to stop sharing for a second so I can change it back to the presentation.
Or is it just removed? Definitely removed.
Don't check on self-move assignment, but self-copy assignment should, I believe.
It may have been moved, it may not have actually been copied.
Okay. Talk about ownership. Oh, we got perfect. We're going to be fine. I haven't got a mouse. Oh, this is going to be interesting. Conceptually, so the owner of an object. This is an important notion. The owner of a dynamic object is a person, the bit of code responsible for deleting it. Right? This is pretty important. So, if you've heard of Rust, if anyone who's played with Rust, Rust the compiler actually enforces ownership, and you have to borrow variables, and it's pretty complicated actually, but the same notions really exist in C++, except you have to get it right. Shared pointers, smart pointers help with that. So, as we've seen, operator new returns a raw pointer. But when we pass raw pointers around, it becomes really difficult to keep track of who owns it. If you pass a raw pointer to a function, how does the callee, let's put it a different way. If you return a raw pointer from a function, how does the person who called that function, how do they know whether they have to delete the pointer that you gave them? Because maybe in your function you said new int, new type, whatever. Right? There is no way of knowing. All they've got to go on is either the documentation, if you're lucky enough that you wrote some, or comments in the code, right? There is no way of knowing, just in the C++ 98 world, in the C world, there's no way of knowing who owns a pointer. So smart pointers are a way of helping us get this right. Does that make sense?
Yeah.
Okay. So, with that, let's talk about unique pointer. Unique pointer is a wrapper around a raw pointer which is called delete in its destructor. This is a slight simplification. It actually has a second template parameter that you can have a custom deleter, but the default is called delete. Supports all the usual operations. You can dereference, member access, conversion to bool. It doesn't actually do pointer arithmetic, but that's a feature. That's a good thing. Unique pointers cannot be copied, right? They can only be moved. We'll see why in a minute. And in C++ 14, there's a function standard make unique to create a unique pointer. It should have been in C++11. It was basically an omission. It's really, really easy to make your own standard make unique function. You can just Google it, or not standard make unique, your own make unique function. So I recommend doing. Right. The one slide introduction. This is complicated, right? So I'm just going to race through this. The one slide introduction to move semantics. This deserves a whole session, possibly a couple of sessions on doing this. A move is an optimization of a copy. Right? Anywhere that you can move, you could do copy, and your program semantically should have the same effect. It leaves a source object in a moved from state. An object in a moved from state, you generally can't do anything with it. You have to look at the documentation to see exactly what you can do with it, because some types will actually let you. But in general, the only thing you can do with it is either assign a new value to it or destroy it. Right, so I was talking about Rust. Rust has all this built in. It won't let you do anything whatsoever with a moved from object. It has a destructive move. This will get people angry. This line, you move an object by calling standard move on it. This is one way of moving an object anyway. So we have this vector v1, and now we're saying v2 equals standard move v1. So what we're doing is we're taking the contents of v1 and we're putting it straight into v2. And now, what does v1 contain?
Nothing.
Well, actually, we don't know.
Should be nothing. So,
Indeterminate.
Yeah.
Undefined.
Yeah, because actually there are funny cases where if you're using a peculiar allocator, then the content is actually still valid, but you can't in general rely on it. So we really can't do very much with v2. If you look at the standard vector documentation, it will tell you can do certain things. You can call dot size on it, but you can't really do anything else. But what this gives us is that we haven't had to allocate in v2 here. We've just effectively stolen the contents of this vector. So remember, vector is a wrapper around a dynamically allocated array. So what we've pretty much done is stolen its internal pointer. That was the one slide introduction. That's it, that's all you get. Standard move, those who are really into this, it's a cast to an R value. We will have a session all about move semantics. I know Ollie was interested in doing it. And this will be explained in vastly more detail. But think of move as an optimization of copy that leaves the object, the source object, in an indeterminate state. So unique points from polymorphism. Well, let's talk about pointer polymorphism for a start. This is the same as, well, pretty much every language that has some form of inheritance-based polymorphism, right? So in Java, you can do, interface I equals new implementation, right? It's the same thing in C++. A base class pointer can point to an instance of a derived class. This is what I was saying about how you do implementation hiding. But when we call delete on the base class pointer, we need the base class pointer to be virtual, because the pointer knows nothing about the derived class.
Base class constructor.
Sorry?
You said base class pointer to.
Oh, the base class, yes.
And sorry, the polymorphism, that means many forms, so different things.
Yes, so this is, we're talking about inheritance, class inheritance and virtual functions, which I promised to do a session of, but we sort of jumped ahead.
Okay.
So
imagine the concept of you have a class that is you create that is called class vehicle. And then vehicle has a functions inside it, member functions, right, called move forwards, move backwards, turn left, turn right. And then, of course, you can have classes derived from vehicle, such as car, truck, bus,
And they'll have access to all this move forward, backward.
And they will implement the actual move forward, move backwards, etc. So then someone who wants to interact with a vehicle doesn't need to actually have the concept of what the vehicle is. So if you apply this to the real world, it's the concept of having, like, imagine if you could make different buses and cars and everything where the driving controls are always the same. So you would learn to drive one of them and you could drive all of them.
That's pretty much that's how it is.
Almost, except for physics, right? That makes it a bit harder, but yeah.
Cool, thank you.
So yes, so we would promise to do a session on inheritance-based polymorphism. So just to show you what this looks like. So we've got a class base to the virtual destructor, so just defaulted because we have no member variables or anything. We've got derived, class derived, which derives from base.
And doesn't have to have the virtual.
It needs, so base, yes, basically.
Okay.
So now we're saying, we're creating a new derived with no arguments, and we're assigning it to a base class pointer. And that's fine, that's perfectly legal to do. And now when we call delete on the pointer, it calls the base class destructor. The base class destructor is virtual, so it does the standard thing for virtual functions, goes through the V table, finds the derived class destructor, which in this case is implicit, but it does the right thing. When you've got base classes, always make the destructor virtual. It's another one of those golden rules, platinum rules. Why do I mention this? I mention this because my computer won't go to the next slide. There we are. The same applies to your unique pointer. You can have, my syntax highlighting didn't get this far apparently. The unique pointer to a base, unique pointer brackets base, can hold a pointer to a derived class. So exactly the same as we just saw. But we still need that virtual destructor. Why do we need the virtual destructor?
Because we have a virtual constructor, and we need to have them virtual destructor, yes? Am I correct?
We don't have a virtual constructor, no.
It's for the delete keyword, right? So when
Yeah.
you put delete on whatever pointer, then it knows which one first.
Because the unique pointer base, it just holds a base star. It doesn't know anything about derived. That information is sort of squirreled away in the what's called the V table, the internals. And that's why unique pointer can't be copied, because although we have a virtual destructor, so when you call delete, it knows which actual destructor to run. There's no such thing as a virtual copy constructor. Right, so when you, if unique pointer was copyable, then what would happen if you tried to copy a unique pointer base? It wouldn't know which derived class it should actually copy. And all you'd get potentially was a copy of base, which actually might be an abstract class that you can't create an instance. That's why unique pointer is not copyable.
Also, if you want the behavior, people will make like a member function called clone, which will give you the new instance.
So yes, this is what I just said, trying to copy a unique pointer base and not know that you need to call the derived class derived copy constructor. And you can get around this by having a virtual clone member function.
Sorry. Great minds. Great minds.
Yeah. This is what, so people have this there's a virtual function clone which is sort of behaves like a virtual copy constructor. So that's a really common thing to do if you want a sort of
Is that not defeating the unique pointer?
No, doesn't care.
No.
It's just a member function that happens to return.
Well, you could make it return
Yeah,
to a unique pointer.
but the whole thing is of unique pointer that you
No,
have
because you can
unique-
have your clone member function return a new unique pointer to base.
So it's like creating like another
Yeah.
object.
But that's what the copy constructor does.
Uh-huh.
The class you just wrote, the copy constructor allocated something new.
Uh-huh.
Copying, we want to create a completely new value, something that is completely separate from the original.
Okay.
Like, this is the value semantics that I talked about a long time ago. Right, and the way to do that is we have to allocate something new. We have to do a new allocation. So the clone member function would hypothetically do that. And in fact, had we had the second example, you would have seen this thing, but I'm sorry, you don't.
I mean, maybe another way to think of it is that, okay, so you get that you have base and then the derived implementation, right? And you can legally say that I'm a derived, but I can be cast to base, yeah? Does that make sense? So this base, I come off of base, so I'm the implementation, this is just a virtual. Right?
Yeah.
So what you can do is you can have a clone method, and you say, I will return a std unique pointer of base. In the actual code, what I do is I copy myself, because I know my own type, right? I'm the derived. So I construct my derived from myself, because I know all my own stuff, all my own code. So I make myself, but I return myself as the base. So anyone who's using me, and obviously the base itself needs to implement the clone as well. You can't just have it in the drive, the base must have it. Then whoever's using it can now say, I'd like a copy of this. Without knowing the derived type, they just call into clone. That dispatches to whatever's derived, and that does all the heavy lifting. Then it just returns it as if it was base. So you just get back your base, which satisfies, all the requirements of base.
But you could do that the same by just normally calling.
No, you can't, because you only know the guy using your stuff only knows base, and base itself isn't copyable because base has no implementation.
Okay.
Makes sense? Ish. Like, okay.
This is,
I think it's better with the example than you see.
So this was we were going to have a class hierarchy to work with. So what we'll do, actually, I think we'll probably talk about it at some point, but when we come back, we'll have one of our group sessions, and we'll have a good exercise.
Yeah, that'll be amazing.
Stuff about shared pointers as well.
Do you like the idea, guys?
Yeah.
Go.
Did you enjoy those? We've had two of them so far. Those little group exercises that we've done. Yeah, sort of.
I mean, if you're sitting silent, we don't know. We assume what we want to assume.
I think one of the ideas was maybe we should just have pairs.
Pairs.
Like, I mean, yeah. I mean, we're fine, yeah.
Yeah.
So if you say we feel better to work in twos, in singles, in one group, whatever, you tell us, and we just arrange that. So we got consent. I think we got the class has spoken.
Silent consensus. All right, that was unique pointer. Let's talk about shared pointer. Shared pointer's the fun one, sort of. Unique pointer model is unique ownership. So we talk about ownership. The owner of something is the person, the bit of code responsible for deleting it. When you move a unique pointer, the old one doesn't have. It's only moved from state, doesn't own it anymore, the new thing you've moved it to. So unique pointer models unique ownership. So what do you think? Shared pointer models?
Shared ownership.
Exactly, yes. So shared ownership, which, how do I put this? Can be overused. So be careful how you use it, but we'll talk about that in a little bit more in a minute. But reference counting. Yes. Oh yes, sorry, one more. We use make shared to create a shared pointer. You can use a shared pointer constructor. It's better 99% of the time to use standard make shared. There are technical reasons for that. It's about one allocation versus two.
We know where you live.
Yeah, exactly. That's the name of the optimization.
Yes,
not just being
that's literally the name of the optimization. Not being creepy. Not being creepy.
A guy who works for Microsoft, whose name I can't pronounce, but who goes by the online handle STL.
Stephen T. Lavaway.
Well done.
Stephen T. Lavaway.
Stefan.
Sorry, yeah, right. It's not Stephen. Stefan. Sorry, I pointed that up. Stefan.
Lavaway or something like that. Anyway, he gives really good talks that you have to watch on about 3/4 speed because he goes very, very fast. But he gives a talk all about why you should use make shared rather than.
I mean, a simple way is basically the case that you have the reference count and you have the object, right? So if you just receive a pointer to the object, so if you use std unique pointer, std shared pointer, new blah blah blah, then now first it's got to allocate memory for the reference count. Then it just takes your pointer and stores that pointer. If you use make shared, now it can just make one allocation, space for the count, space for the object. And it's all one allocation rather than two, one for the count, one for the object. That's it.
So quick diversion about reference counting. We had a quick diversion about move semantics. We're having another quick diversion. You're lucky we were going to have a quick diversion about class templates, or one slide introduction to class templates, but in the end we didn't, so don't worry.
Teasing.
So when we create a shared pointer, its initial reference count is 1, right? So the reference count is how many things have shared ownership of this shared pointer. When we copy a shared pointer, we're creating a new one. So when we run the copy constructor, we're creating a new instance, right? So we increment the reference count. It means we've created the copy, so now 2 things own this. There is a reason I was going through this, is because I was going to get you to implement something very similar, a shared pointer, but it didn't work out, but never mind. When we destroy a shared pointer's reference count, it's decremented. When the count hits 0, it means the last object has been destroyed, and the object can be freed. Right, so a reference count of 0 means nothing is holding a reference, effectively nothing is holding a reference to the contained object. We can be freed. I said freed, I should have said destroyed.
The first bullet point, when we create shared pointer, so if it doesn't point to the object, I think it should have the reference count equal to 0. If it's not a pointer, for example. Only if we initialize it to point to some object,
That's true.
then it will have counts to 1.
Yeah, that's true.
Ollie thinks you're right. So
If there's nothing to track, if there's nothing to track, then there's no need for a reference count.
And for the slide says create.
When we create a shared, when we run the shared pointer constructor, or call make shared, which runs the shared pointer constructor in the background.
I don't understand.
So you can create a shared pointer that points to nothing. In the same way you can declare a pointer like a T star equals null pointer, you can do shared pointer T equals null pointer. So it's a shared pointer to nothing. It's a shared pointer to a 0 value, to a null value.
That would initialize the reference count to 0.
I suspect it probably, as an optimization, you probably wouldn't even create the reference count.
No, because you'd have to, because you could.
If
you could reset, it's called .reset on the shared pointer.
The thing is, you can't technically have your own storage of the reference count. If you null pointer construct it, then do the assignment operator from make shared, it's going to have to inherit that whole control block and everything, because the deleter is also type arrays. So I would say a default constructed one will have literally.
That's a very good question. We're going to talk about.
Yeah.
Two good questions.
Carry on with the presentation. Yeah.
Yeah. Well, you've thrown me off my scent now. All right. So bonus points. So you three, this panel of experts that are judging me down here.
No.
Don't answer this.
Jesus.
What happens to the reference count when we move a shared pointer? So when we copy a shared pointer,
It will decrease.
When you move it, nothing happens to the reference count.
what did I just say?
Oh, fuck, sorry. I tell you what. Never mind. I'm just going to shut up.
He's right though. Annoyingly. When we move a shared pointer, nothing happens to the reference counts, right? Because we've just stolen the contents, including its reference. So the shared pointer we have moved from is now effectively unusable, right?
So practically speaking, then it should actually be lower because you can't use it.
No, but we've still created a new object.
Yeah.
Right? So if you think about it, let's say we have shared pointer A, and then we create a pointer B. We do shared pointer B equals standard move A.
Yeah, but then A will become like
like a
void. Almost.
A has given up its reference, but we've created a new object B, which needs a reference, which needs above the reference count. So A's.
So basically, okay. So what I was thinking, like, so you don't have 2, yes, because A become B, so A is basically obsolete. But then in that case we have B.
Yeah. So, so A is giving up its reference, so that lowers the reference count, but we've created new object B, which increases the reference count. And actually, it sounds silly, but you do have to be very careful when you're implementing these things that you don't accidentally do these things in the wrong order and have your reference count drop to 0 and the object is destroyed in the meantime.
Just to understand, if we have two shared pointer objects, do they share that memory where they're storing that
Reference count?
Reference count,
Yes.
that control. So it's the same. So no matter how many shared pointer
instances, yes.
you create,
Yes.
they will share the same control structure.
Yes.
But there is one important distinction, which is that if you say you have two different guys, well, I'm making this humanized now, but one guy's got a shared pointer, the other guy's got a shared pointer to the same thing.
Yes.
So they're both sharing the same thing. One of them calls reset. So he says, I'm done with this. I'm going to make this shared pointer do something new. Are you going to cover this?
No, go ahead.
Okay. I'm going to cover something new. That does not affect the other guy. When he calls reset, he drops the reference count by 1, and he'll assign his shared pointer to whatever new object he's going to use. But the guy over here is completely unaffected, and he will continue using that object, and it will not be deleted. There are different pointer types where they can have intrusive pointers. It's not part of C++.
Boost has a whole load of other shared pointers with slightly different properties.
Yeah, different semantics basically. There's I think it's intrusive pointer where if one of your threads, for example, one of your consumers calls reset, everybody sees it. For shared pointer, that's not the case.
So if you have, let's say, in your example, count 2, yes, and one of them calls reset, so he starts pointing somewhere else, I understand.
The count just drops to 1, that's it.
Yeah, okay. Fine.
Just a silly question.
Yeah.
What if you have a reference to a shared pointer? Does that change the internal reference of the shared? No.
No, so reference types to anything is a fundamental C++ type, and you're just saying that I'm using this thing and it's the same thing.
Okay.
Yeah. It's rather unfortunate we call it a reference count because that's the name, but it's nothing to do with C++ references.
Yeah, it's separate.
Yeah, it's a bit unfortunate that.
Think of it as a usage count.
Use count. Yeah. Use count would be better name, but the standard name for it is reference count.
Yeah.
Oh yeah, beware of
I'll put
cycles.
this down. I was hoping you. Yes.
I just said beware of cyclists.
I was going to put a little logo up and it, but then I thought that would be childish. Right. This is somebody asked a question about this. Reference counting can be thought of as a simple form of garbage collection, probably the simplest form of garbage collection. So Python, Swift, I don't know what else. At least,
Java?
No, Java's got a very, very sophisticated garbage collection, but Python and Swift at least, their garbage collection actually just uses reference counting. But Python also has a cycle detector. It's easy to get into a situation where two objects hold references to each other, right? And this can be a very indirect. If you think about like a graph data structure, you can have links between nodes pointing all over the place, and you can end up with a cycle. And this prevents the objects, they're all keeping each other alive. So A holds a shared pointer to B, which holds a shared pointer to C, to D, back to A. They're all keeping each other alive. We've got a cycle. We have a memory leak, right? Because these things will never be destroyed. That's a problem. Really beware of cycles. We've got 2 slides on it. This was a known problem when they came up with shared pointer. It's not a new thing. There's this facility called weak pointer. A weak pointer is a weak reference to a shared pointer, if you like. So we create a weak pointer from a shared pointer, but a weak pointer doesn't increase the shared pointer's reference count, right? It's aware of it, but it doesn't keep it alive, right? That's why it's weak. It doesn't keep the shared pointer alive. We pretty much can't do anything with a weak pointer except call .lock on it. So it's got a lock member function. And if we call lock, it will return us a shared pointer to the original thing. It will strengthen the weak pointer temporarily, to allow us to call methods on it, right? But if in the meantime the shared pointer has been destroyed, lock will, if so, I have to say exactly, if the shared pointer has been destroyed, then lock will return an empty object. So you call .lock, it will return you a shared pointer. You check whether that shared pointer contains a value, and if it does, you're good, you can call methods on it, otherwise you know it's died. Right, so weak pointer is useful for breaking, well, the point of it is to break reference cycles. This sort of reference cycle, by the way, it can happen in garbage collected languages as well. It's a bit harder to have, but you can hold on to references in Java for longer than you should and keep it.
There was some issues with the weak pointer, because I've seen some of the articles when they share pointer to a weak pointer prevent from completely freeing the memory.
No, what you're thinking about is a control block. So the weak pointer
keeps the control block alive.
Yes. So the weak pointer, the control block itself has its own reference count that is separate from the object's reference count, and the weak pointer does keep the control block alive because it has to know where the shared pointer is to call .lock on it. Right. So that's probably what you read. And actually, that's one reason why. Sometimes, in very narrow cases, you might want to avoid make shared because make shared uses a single allocation, which in a lot of cases is an optimization. But if you're using weak pointers heavily, then this can end up keeping a lot more memory alive than you actually wanted to. Yes.
Is weak pointer a subclass of shared pointer?
No.
No.
It has a constructor parameter type that is a shared pointer, but it doesn't derive from it. Also, to give you an example of a real world use case of this, right? You might have, say, some thread. Do you want more Guinness? You might have, say, you might have some thread that you expect to take, say, 5 seconds to complete a job. So you can give it a shared pointer of some type that's going to do the work, some class that's going to do the work. But the idea is you want it to do it in 5 seconds. So you have another thread that acts as a timer. So what you want to do is your timer thread will activate after 5 seconds, right? Or you'll use some OS feature to activate it after 5 seconds. And what you'll want to do is give it a weak pointer to the class doing the work, because after 5 seconds it wakes up, and then you can just call .lock. And if the other thread has done everything normally and everything's good, then your weak pointer won't lock because it did what it needed to do. Great, do nothing, just let the thread leave. On the other hand, if it does lock, okay, we need to kill this, and then you can call a method or destruct it, whatever it is, to then cancel that operation.
Cool. So threaded operations are one of the major uses of shared pointer, right? Because you don't know how long this thread is going to keep running. It may not, the operating system may not schedule it for ages, and shared pointers let you keep this object alive and let you share an object between threads, and each thread can keep the object alive, and you don't have to worry about thread A finishing first, kills the object, and then thread B crashes. But yeah.
Is dependency injection another example? I mean, another frequent use case when shared pointers is used?
I'm not really sure what you mean by dependency injection.
For example, if we have one class depending on another, and so class A is using class B, and if we pass it by just a pointer, then again we have this problem of the shell. Class A could destroy class B.
Yes.
Class B might be used by class C as well.
Yes.
And I mean that's what I was reading, that shared pointers are used as a way of.
I will defer to you on that.
Dependency injection.
I kind of asked DI or dependency injection, sort of a big thing in Java, right? The closest you're really going to come to the concept of dependency injection in C++ is the concept of an interface class, a class of pure virtual functions and then derived types. And to be honest, that's essentially independent of shared pointer. you can have shared pointers to some virtual base, and it works fine. Maybe what you're thinking of that the benefit is that because shared pointer uses type erasure for the deleter, you can have a shared pointer to some base, and then you can make shared on the derived, and because the actual base type, because the deleter is type erased, you don't need a virtual destructor. So you can have a base of a non-virtual destructor called make shared on the derived, and it will still clean up without memory leaks. Whereas obviously unique pointer does not have a type erased deleter. It would leak memory if you did that. You must, if you're going to use unique pointer, your base must have a virtual destructor. It does not have to have a virtual destructor for make shared and shared pointer.
How come the, I mean, best suggestion, I mean, I'm coming more from C# world.
Okay.
Very frequently used.
Basic thing is Java, yeah.
Yeah. But I'm now a bit confused because I haven't seen DI much used or mentioned in C++ world. So I'm a bit
The
confused.
thing is that, by the way, you can usually use DI in Java and C#, there's also a reflection, which we don't really have in C++. So for the concept of DI, you will literally take some jar or some assembly, right? And it will satisfy some interface, and you can literally just use that at runtime through reflection. We don't have that in C++, so again, the closest you'll get is interfaces.
That's not my field of expertise. I'll let Ollie argue with you.
It's very frequent. That case, you know, when class A is using class B.
Yeah.
How would you pass the reference like in generic term? Would you
Okay, well, first of all, if you can...
pointer or a reference or a spark pointer?
Right. Well, exactly. If only there was a guideline that to appear on your screen. In general, you use shared pointers when you want to keep something alive, right? Or when you have genuinely shared ownership of something.
Or if you are not sure who's gonna delete.
Yeah, exactly. So in the threaded case, because you know you don't know when things are going to finish, but everything needs to use the same bit of data.
That's what I mean, because if class A is using class B, so class B has been created by someone.
Yeah.
And that someone is the owner because
yeah.
you would expect that guy will destroy it. You just want to use it.
Okay. In that case, if you know for a fact that B is going to stay around for the whole time that you're around, then you just use a raw pointer or a reference.
Yeah, how would you use it?
You as a user of that B, you say, oh, I don't know who is creating it. I don't know who is destroying it. I'm not interested in destroying it. I just want to use it. Mm-hmm. And in your API, you'll say, I want to share the pointer to B, to dependency. I mean,
the shared pointer should not be the first tool you reach for. So I'm going to say a little bit more in a second. Try and solve it. If you need to use dynamic allocation, if you're doing runtime polymorphism, you know, virtual functions and everything, reach for unique pointer first. And only if you need to use a shared pointer, then use one. So there's a very well-known guy by the name of Sean Parent, who does lots of really, really good talks on C++. He likes to say that a shared pointer is as good as a global variable, and global variables are kind of bad because you never know who's going to change it and when, right? Whereas your unique pointer, you know who owns it. So you want to try and have well-defined lifetimes. So you want to know that if class A uses class B, you want to know that B is going to stick around for at least as long as A is alive. In which case A can just use a raw pointer or a reference if you know it's never going to be null. Right? Only if B might be ephemeral, might disappear at random times, then it might be appropriate for A to keep it alive with a shared pointer. You really don't seem convinced about this, are you?
Yeah, well, I'm just thinking, if someone reads the code, would they know, I mean, for example, if I'm operating with a shared pointer, somehow I know that I should not delete, I should not, I'm not the owner. If I have a unique pointer, then it means that I'm the owner, I can delete the object. It's like,
Well, with a unique pointer, again, you shouldn't be using. A unique pointer is going to have a well-defined lifetime because you're going to allocate it on the stack. It's going to be an automatic variable. It's going to go out of scope, and then it'll die. But hopefully, the scope of things that use it are narrower, right? So they're within functions buried in your stack. So this, yeah, sorry.
I was just going to ask if you're writing a data structure that uses pointers,
Yeah.
like a list or which is preferable, unique pointer or shared?
Unique pointer. So use unique pointer to model unique ownership. So for something like a linked list, conceptually anyway, you have every node would have a unique pointer to the next one down the chain, but have a raw pointer back. Because otherwise you get cycles, which would be bad. Or conceptually at least, I think probably standard list is a lot more confusing. Right, we've only got a few more minutes. So this, I believe, is the last slide. So this is pretty much perfect. This is the second. How many important bullet points have I had today?
Quite a few.
Right. Well, this is a good one. Never use new or delete. I've just made you do a whole exercise on it. I was going to make you do another exercise all about smart pointers, but actually we've worked out right time-wise. So yeah. Never use naked new or delete. Right. I said in C++ 14, the only reason I said 14 and not 11 is because 11 doesn't have this make unique function. The only time you should use new in C++ 11 is if you're going to give the pointer to give the return value to a unique pointer constructor. Always use smart pointers to containers. Right. There is one little exception to this, a little caveat, which is if you're using Qt, because Qt is very old. And Qt requires you to say new and then give the pointer to your parent class and whatever. So there's a little caveat if you're using the Qt framework. But yeah, basically, never use new or delete. Unique pointer, that's what I was saying, should be your default go-to smart pointer class. Use shared pointer rarely, and only when shared ownership is genuinely required. So there's a big temptation, particularly from people who come from the Java or C# world, and I think maybe where we're coming from here is you got shared pointer. Well, that's basically garbage collection for C++, right? Oh, that's brilliant. I can just make everything a shared pointer. I never have to worry about deleting everything. You know, I might have to be a little bit careful about cycles, but brilliant. The problem with that, and it's a thing I haven't actually mentioned, is that shared pointers reference counting. Updating the reference counts is actually quite an expensive thing to do. It uses atomic operations so that all threads see the same value of the reference count at the same time. And so actually, copying shared pointers about all over the place is not as cheap as you might like it to be. And so in fact, if you do end up using shared pointers everywhere, you can end up with worse performance than you've got in Java, because Java has a very, very sophisticated garbage collector, much more sophisticated than just reference counting. So if you try and use shared pointer as a sort of proxy for garbage collection, you're probably going to be unhappy. Right, so use it. There are genuine cases where you need to use shared pointer, but it shouldn't be your first go-to, right? And use raw pointers only to represent unowned objects. Right? This is paired with this. So if you see a smart pointer, you know that represents ownership, either unique ownership or shared ownership. If you see a raw pointer, if you see T star, it means this is unowned. I do not need to delete this. You still might have to check whether it's null, but it means I don't have to delete this. It's like, effectively, in modern C++, in new versions, a raw pointer is just a nullable reference, unless you're doing sort of low-level work. Anyway, look at that, 5 to 9. We've actually done everything. Sorry, yeah.
If we have, let's say, unique pointer, can we, I don't know, access this as the raw pointer?
Yeah, so there's a .get member function that gives you the internal raw pointer.
And is that good, advisable?
Yeah, so if you've got an API that needs you've got a unique pointer T, unique pointer int, say, and you've got an API that uses an int star, you just call .get on your unique pointer. Okay. We'll give you a copy of the internal pointer.
But the catch is that the semantic must be non-owning. There are plenty of APIs that will take a pointer and then they expect to take ownership of it and delete it, which obviously will be bad if you give them the raw pointer.
But there's a .release function. Unique pointer has a .release function that says, here's the pointer, and I'm not going to delete it anymore. Now it belongs to you. So .release is a way.
So how does that API knows that you're releasing?
Well, I think what Ollie's talking about is sort of older C++ 98 code where you had. So this is for modern code. We have this convention that a raw pointer is unowned. Older C++ 98 code didn't have that convention, and you can have APIs where it says, all right, pass me the pointer, and I will take ownership of this pointer, and I will call delete on this pointer, which is in fact exactly what Qt does, which is why I said it's an exception.
I'm just wondering, in the old C++ 98 style, can we enforce, can we forbid deleting the pointer if we pass const pointer? I mean, or that, I mean, the question is it possible to delete const pointer? But I believe it's possible. I'm not sure.
Yes.
It is possible.
I believe so.
So it's not enforced.
T-star const.
Not pointer to const object, but const pointer.
Yeah, you can. You should be able. You have to be able to delete a T-star const because I could allocate a T-star const, so I have to be able to delete a T-star const.
Yeah. So that's not enough.
No. Anyway, that's it. It turns out we didn't need any more, did we? So
Excellent.
just for those who are, if there's anybody left, they probably all gone away bored now. But we have all these online resources. I'm going to put the slides up on the GitHub. And yeah, thank you for coming. That's how to contact us.
Perfect.
Thank you very much.
Thanks, everybody. The next session, as you know, or I hope you know, it's the 9th of January. Now, it's planned to be in the code node, but if you're happy and we've got the facility to record, I might talk to the code node, and if Olio says yes, he is allowed to host us here, then we might switch to here because we've got the facility to record and obviously get some people as well from outside. We had one guest from Nigeria. Hopefully we'll get from other places as well. Now, as usual, we need your input. So if you have any ideas how we can make this, this meeting better, let me know. Because if I hear the, like silence, I assume the answer myself. Or Tristan, yes. Neither of us is probably the best qualified for assuming, yeah. So we need your help. Now, after this meeting, we are going to a pub. You're very welcome to join. It's no pressure. We'll not twist anybody's hand behind it if you don't. But it would be a good idea to pay these guys, a bit of respect and buy them a beer or two. And if I don't see you before Christmas, I wish everybody Merry Christmas, Happy New Year. Enjoy the time with your family, and thanks so much for coming.
Hi.